This is quiz 25, and these are a bunch of problems over L'Hopital's rule, or calculating limits where you've got some kind of discontinuity involved. So number one, we're taking the limit as x goes to 1, and you first do a reality check and plug in 1 and see what happens. Obviously in the bottom, 1 minus 1 is 0, and in the top, you get 1 minus 2 plus 1, which is also 0. So this is a 0 over 0 indeterminate form. L'Hopital's rule applies if we want to use it, and since this is the limit as x approaches 1, yeah, we will go ahead and do this and see what happens. So as x approaches 1, the limit as x approaches 1 of this fraction by L'Hopital's rule, since this is a 0 over 0 indeterminate form, would be the same as the limit of the derivative of the top divided by the derivative of the bottom. So the derivative of the top, of course, is 3x squared minus 4x. And on the bottom, we have 3x squared all alone. Now we check and see if we can calculate this limit, and as x approaches 1, we see that the bottom is not going to be a problem at all. So this limit can be done right away. Limit as x approaches 1, the bottom goes to 3. The top is 3 minus 4, so that's going to be negative 1. So the answer to number 1 is negative a third. Number 2, we check out what happens again as t goes to 0. As t goes to 0, sine of 0 would be 0, so the bottom is going to 0. The top, e to the 2 times 0 would be e to the 1, which is e to the 0, which is 1. 1 minus 1 is 0. So the top goes to 0 too. So we have a 0 over 0 indeterminate form. Once again, L'Hopital's rule applies. So we can take the limit by calculating the derivative of the top and the derivative of the bottom and taking the limit of that. So we're trading this limit problem for the limit of a different problem. Derivative of e to the 2t would be e to the 2t back again, except the chain rule has something to say, because 2t is not t, so we got to multiply by the derivative of what's up there. Then minus the derivative of 1, that's not going to be a problem, 0. Derivative of sine becomes cosine, and so now again we try plugging in 0, and we see that the bottom is going to turn into 1. And in the top, as t goes to 0, we get e to the 0, which is 1 times 2, so we just end up with 2 over 1, which is of course 2. Okay, number 3, as you plug in 0, you see that the bottom goes to 0 plus cosine of 0. But cosine of 0 is 1, so the bottom is going to 1. So really, this is not an indeterminate form no matter what happens to the numerator. Because if the bottom goes to 1, we can tell what's going to happen no matter what goes on up here. And in this case, as x goes to 0, the first goes to 0, the second goes to 0, so the answer is just 0 over 1, which is no problem at all, 0. L'Hopital's rule does not apply. I think this problem would be very bad for you if you use L'Hopital's rule. This is not a 0 over 0 situation. And if you use L'Hopital's rule, you'll get the wrong answer, undoubtedly, because the derivative of the top is going to be 1 plus cosine, and the bottom, you're going to get 1 minus sine. So as x goes to 0, you're going to end up with something like 2. But this function very definitely gets close to 0 as x approaches 0. There's no problem with this. It's 0 over 1. Okay, next problem. As x approaches infinity, obviously x gets large. Here we have to think about it a little bit. As x gets large, pi over x is getting small. So that goes to 0. And as the argument of the sine goes to 0, sine of something goes to 0, also goes to 0. So this term is going to 0 while this term goes to infinity. So we're dealing with an infinity times 0 situation. And this is an indeterminate form. You can't tell who's going to win this. Depends on who's going faster. Is x going to infinity faster than the sine is going to 0? Or are they both going at about the same rate, so there's going to be some other limit? Well, you can't tell, so you have to do more work. So we turn this into a quotient so that L'Hopital's rule can apply, and we can put either one of them on the bottom, but it seems to me that it makes much more sense to put x down on the bottom. So this is going to be the sine of pi over x on top, And on the bottom, x pushed down to the bottom becomes 1 over x. Just do a quick check on this. If you simplify this fraction, multiply top and bottom by x, you will end up with that. Okay, now the reason for doing this is because L'Hopital's rule applies to this fraction, because as x gets large, the bottom goes to 0, and so does the top. So this is a 0 over 0 indeterminate form. So L'Hopital's rule says that as x goes to infinity, you can take the limit by taking the derivative of the top and the derivative of the bottom. Okay, so the derivative sine of anything is cosine of that anything. So you get pi over x. Cosine of pi over x. But the chain rule says you got to multiply by the derivative of what's inside. The derivative of pi over x. Well, if you look at pi over x as pi times x to the negative 1, then the derivative of that is going to be minus pi x to the minus 2, which I would rather write as minus pi over x squared, for reasons that become clear in a moment. Because the derivative of 1 over x is also minus x to the minus 2, or minus 1 over x squared. So that makes it easy to simplify this thing. So if you just rewrite this, the limit as x approaches infinity of what? Multiply top and bottom by x squared and by minus 1. So what you're going to end up with is pi, because nothing canceled that out. The x squareds are gone, and you've still got a cosine of pi over x. And on the bottom, there's nothing left. So we're just dealing with this. Okay, as x gets large, pi over x goes to 0. Cosine of 0 will be 1, so this just ends up being pi. Okay, that takes us to number 5, which is this nasty exponential expression. As x gets large, the base is going to infinity, but the exponent is going to 0. So we've got an infinity to the 0. And this is an indeterminate form, because as the base gets large, you expect the answer to get large. But if the exponent's going to 0, you expect the answer to get small, get close to 1. So you can't tell what's happening here. So we need to rewrite this. And so the technique that we use is we say let y equal x to the 1 over x. And then we hit both sides with the log, natural log. So we get natural log of x to the 1 over x, which we can then rewrite according to the laws of exponents, because that exponent plays well with the log. So it comes tumbling down, leaving us with 1 over x, ln, not limit, ln of x. Okay? So this is the log of y. We're no longer dealing with the problem at hand. We're dealing with the log of y, and we'll have to remember that later. Okay, so this is 1 over x log of x, which we can rewrite as log of x over x. So we can now ask the question, what happens to the log of y as x goes to infinity? In other words, what is the limit as x goes to infinity of not y, which is what we want, but the log of y? And the answer is it's the limit as x goes to infinity of log x over x. And as x gets large, bottom obviously gets large, numerator also gets large, somewhat slower. But L'Hopital's rule then applies, because this is an infinity over infinity indeterminate form. So we can take the limit by calculating the derivative of the top and the derivative of the bottom. So derivative of log, of course, is 1 over x. Derivative of x is 1. And so now we take the limit of this as x approaches infinity, and that's clearly 0. So what do we know? We know that the log of y has a limit of 0. So we can write it this way. The log of y goes to 0 as x goes to infinity. But now we remember that it's not really the log of y that we're interested in. We were really interested in y. So how do we get back to that? Well, we have to exponentiate to kill off the log. So e to the log of y goes to e to the 0, because the exponential function is continuous. You can remember that. And so This, of course, reduces to y, and y goes to e to the 0, which is 1. So the limit of this quantity is equal to 1. And that is it for quiz 25.